Black holes are among the most mysterious and powerful phenomena in the universe. Unlike ordinary celestial bodies such as stars or planets, a black hole is not a solid object with a visible surface. Instead, it is a region of spacetime where gravity becomes so extreme that nothing can escape once it crosses a certain boundary, not even light itself. Because they emit no visible light, black holes cannot be observed directly in the traditional sense. Their existence is revealed only through the effects they have on nearby matter, radiation, and the structure of spacetime around them. At the heart of every black hole lies a concept known as the singularity. This is believed to be a point where matter is compressed into an infinitely dense state and the known laws of physics no longer function properly. In this region, gravity becomes so intense that our current understanding of space and time breaks down completely. Scientists consider the singularity one of the greatest unresolved mysteries in modern physics because existing theories cannot fully describe what happens there. The scientific foundation for black holes began with the development of the theory of general relativity by Albert Einstein in 1915. Einstein transformed humanity's understanding of gravity by explaining that massive objects bend the fabric of spacetime itself. According to this theory, gravity is not simply a force pulling objects together, but rather the result of curved spacetime created by mass and energy. Shortly afterward, physicist Karl Schwarzschild discovered a mathematical solution to Einstein's equations that described an object dense enough that its escape velocity would exceed the speed of light. Initially, this idea was treated as a theoretical curiosity rather than a real cosmic object. For many years, black holes existed only in mathematical equations and scientific speculation. As astronomical technology improved during the 20th century, evidence supporting the existence of black holes began to emerge. One of the strongest early clues came from X-ray observations of binary star systems. In some systems, scientists observed visible stars orbiting invisible companions with enormous gravitational influence. These unseen objects were too massive to be neutron stars or other known stellar remnants. One famous example was Cygnus X1, where a bright star appeared to be orbiting a hidden but extremely massive object. Gas pulled from the visible star formed a rapidly spinning accretion disk around the unseen companion. As the material spiraled inward, friction and gravitational compression heated it to millions of degrees, producing intense X-rays detectable from Earth. These observations provided convincing indirect evidence that black holes truly exist. Scientists eventually realized that black holes are not merely cosmic destroyers. They play an important role in shaping galaxies and influencing the evolution of the universe itself. Nearly every large galaxy appears to contain a supermassive black hole at its center, with masses millions or even billions of times greater than the Sun. These enormous objects affect the movement of stars, the distribution of gas, and the formation of new stellar systems. At the center of our own galaxy, the Milky Way, lies the supermassive black hole known as Sagittarius A. Although invisible directly, its presence is confirmed through the motion of nearby stars orbiting around an unseen gravitational source. This hidden giant quietly controls the dynamics of the galactic core. Black holes remain difficult to observe because they produce no light of their own. Instead, astronomers study how matter behaves near them. Material falling toward a black hole forms an accretion disk that rotates at extremely high speeds. These disks can become so energetic that they outshine entire galaxies. Surrounding the black hole is the event horizon, the boundary beyond which escape becomes impossible. Near the event horizon, gravity produces extraordinary effects. One of the most dramatic is known as spaghettification. Because gravity becomes much stronger closer to the black hole, objects experience intense stretching forces. An object approaching too closely would eventually be pulled apart into long, thin structures before disappearing beyond the event horizon. Another remarkable consequence of extreme gravity is time dilation. According to relativity, time slows down near a black hole relative to distant observers. These effects demonstrate that black holes are not simply massive objects in space but profound distortions in the structure of spacetime itself. A historic milestone in black hole research occurred in 2019 when the Event Horizon Telescope collaboration released the first direct image of a black hole shadow. The image captured the supermassive black hole at the center of the galaxy Messier 87, located approximately 55 million light-years from Earth. The picture revealed a bright ring of glowing plasma surrounding a dark central region corresponding to the event horizon. This achievement transformed black holes from theoretical predictions into directly observable cosmic realities. Just outside the event horizon lies the photon sphere, a region where gravity is strong enough to force light itself into curved orbits. In this area, photons may circle the black hole temporarily before escaping or falling inward. Such phenomena illustrate the extreme conditions that exist near black holes and show how even light is affected by gravity under these circumstances. Despite major scientific advances, black holes continue to raise profound questions about the nature of the universe. At the center of these mysteries is the singularity, where general relativity and quantum mechanics appear to conflict. General relativity successfully describes massive cosmic structures, while quantum mechanics explains the behavior of particles on the smallest scales. However, inside black holes these two theories become incompatible, creating one of the greatest challenges in modern science. To solve this problem, physicists are searching for a unified theory of quantum gravity. One important candidate is string theory, developed by researchers including Edward Witten and others. According to this framework, fundamental particles are not tiny points but microscopic vibrating strings of energy. Different vibrations correspond to different particles and forces, suggesting that all matter in the universe emerges from underlying patterns of vibration. String theory also proposes the existence of additional spatial dimensions beyond the familiar three dimensions humans experience daily. These extra dimensions may be compact and hidden at scales far too small to observe directly. Although experimental confirmation remains absent, the theory offers possible explanations for some of the paradoxes associated with black holes. One of the most famous unresolved problems is the black hole information paradox. Quantum mechanics states that information about physical systems cannot be permanently destroyed. However, if matter disappears completely inside a black hole, it seems that information may be lost forever. This contradiction challenges fundamental principles of physics and remains an active area of theoretical research. Another fascinating category of black holes involves rotating black holes, described mathematically by the Kerr solution to Einstein's equations. Unlike non-rotating black holes, these objects possess angular momentum, causing spacetime itself to twist around them in a process called frame dragging. Rotating black holes create a region known as the ergosphere, where the rotation of spacetime becomes so powerful that nothing can remain motionless. Some theoretical models suggest that energy could potentially be extracted from this region through a mechanism called the Penrose process. While highly speculative from a technological perspective, this concept demonstrates the extraordinary physical possibilities associated with rotating black holes. Even more speculative are wormholes, theoretical tunnels connecting distant regions of spacetime. Certain solutions to Einstein's equations suggest that such structures could exist under extreme conditions. If stabilized using hypothetical exotic matter, wormholes might theoretically allow shortcuts across enormous cosmic distances or even create paths through time itself. However, there is currently no observational evidence proving that wormholes exist in reality. The study of black holes entered a revolutionary new phase in 2015 with the detection of gravitational waves by the LIGO Scientific Collaboration and Virgo Collaboration. These waves are ripples in spacetime produced by massive cosmic events such as black hole collisions. When two black holes spiral together and merge, they release enormous amounts of energy in the form of gravitational waves traveling across the universe at the speed of light. Detecting these signals allowed scientists to observe cosmic events through an entirely new method. Instead of only seeing the universe through electromagnetic radiation such as visible light or X-rays, researchers could now listen to the vibrations of spacetime itself. Each gravitational wave detection provides valuable information about black hole masses, spin rates, and population distribution throughout the cosmos. These discoveries have opened an entirely new field of astronomy and deepened humanity's understanding of extreme astrophysical phenomena. Today, black holes are recognized not as simple cosmic voids, but as essential components of galactic evolution in powerful laboratories for studying the laws of physics under extreme conditions. They influence star formation, regulate galactic structures, and test the limits of scientific theory. As technology continues to improve through advanced telescopes, detectors, and computational models, scientists move closer to answering some of the deepest questions in existence. Yet black holes remain profoundly mysterious. They exist at the boundary between the known and the unknown, challenging our understanding of reality itself. Even after decades of research, black holes continue to inspire curiosity, philosophical reflection, and scientific exploration. They remind humanity that the universe is far more complex, powerful, and mysterious than we once imagined.